Welcome back to the Deep Dive. Today, we are strapping on our virtual helmets and heading into the ultimate training ground for security professionals and ethical hackers.
We're talking about capture the flag challenges, or CTFs.
Exactly. If you really want to move beyond the textbook and see how the pros practice, this is where you go.
That's right. And our mission today is to do a deep dive into the source material that lays out the essential tools and the fundamental concepts you need to not just play, but actually succeed in these environments.
Think of it like a blueprint for the hacker's brain.
Yeah, that's a good way to put it.
And when we talk about a CTF environment, we should probably clarify what that means right away. It's not just solving some riddle in a sandbox, is it?
No, not at all. We're almost always dealing with a targeted client-server architecture. The flag, which is just, a fancy term for a password or secret you need to find, is sitting on a remote server.
And your job is to get it.
Your job as the client is to find a vulnerable program on that server, exploit it, and capture that flag remotely. It takes a lot of technical finesse and a very specific toolkit.
Okay, and before we unpack that toolkit, I think we should mention the resources here. For anyone just starting out, there are platforms like CTF, Pico CTF, and for a big overview, the official CTF handbook.
And those sources really point us to the tools that are, well, non-negotiable.
So where do we start?
We have to start with the foundational utilities. Let's call this the hacker's Swiss Army knife, and it begins with a tool called Netcat, or just ANSI.
Okay, let's break this down. Netcat is foundational, but what is it actually doing that makes it so critical?
Well, its core utility is deceptive in its simplicity. It's a command line networking program for reading from and writing to network connections.
So using TCP or UDP.
Exactly. It lets you treat a network socket just like a file. You can pipe data into it, you can read data out of it. It's the simplest way to manually create network traffic without writing complex code.
And the sources point out a really surprising use case, especially in these low-resource CTF environments.
Yeah, you can use it to transfer files between computers. It's perfect when you don't have access to, normal file sharing protocols.
Right, and critically, it's used to simulate the target CTF server while you're developing an exploit.
You can set up Netcat to listen on a port and then run a binary, let's say, the vulnerable program, vuln.exe, anytime a client connects. This lets you test your exploit locally, over and over again.
But there's a catch, right? I remember reading about a practical snag that everyone hits with this simple setup.
There is, and it's incredibly annoying.
If I'm developing an exploit, I might need to run it, crash the program, tweak my code, run it again. Does Netcat handle that well?
No, it doesn't. By default, Netcat just stops listening after that first client connection is done. Whether it succeeds or the program crashes, it just quits.
So you'd have to manually restart it every single time.
Every single time. Imagine doing that hundreds of times. It's a productivity killer.
So what's the workaround that the sources provide?
It's an elegant one. You use a bash script wrapper, often called something like a Netcat loop.
And that just loops.
It creates an infinite loop that just restarts Netcat every time the program exits. It forces the server to keep listening, ready for one connection after another. It seems small, but it's absolutely critical for development.
So Netcat gives you the stable pipe. Now you need the heavy machinery to build what goes through that pipe.
And that brings us to Pwntools.
This isn't just a generic Python library, right? It's built for this.
It is the bespoke framework for exploit development in these CTF settings. It dramatically cuts down on the effort you need for scaffolding, encoding, and managing the connection.
And before you even write an attack, Pwntools has a vital first step, the checksec command. What are you looking for with that?
You're looking for the program's built-in defenses. You point checksec at a binary, like our vuln.exe, and it instantly tells you if key security controls are enabled. The big one is ASLR.
Address space layout randomization.
Exactly.
And just as a quick refresher, why does ASLR ruin a simple attack?
Well, a simple memory exploit relies on knowing the exact memory address of something, like the return address on the stack. You need that address so you can overwrite it.
And ASLR shuffles those addresses.
It shuffles the locations of key data areas in memory every single time the program runs. So your exploit, which is pointing to a fixed address, suddenly points to junk data. The program crashes and your attack fails. Checksec tells you upfront if you have to deal with that.
That makes perfect sense. So once you know the security, Pwntools is all about convenience for remote testing. What info do you need to plug into it to get it talking to the server?
You just need the program name, the IP of the host, which could be a 127.0.0.1 for local testing, and the listening port.
The sources mentioned using unreserved ports, right?
Yeah, anything above 1024 to avoid conflicts. For a real contest, you just use the IP and port they give you. Pwntools handles all the low-level socket stuff seamlessly.
Okay, let's zoom in on the workflow because Pwntools doesn't just run the exploit. It helps you build it.
It does. It generates an exploit.py file that's filled with boilerplate code.
And what's the biggest time saver that boilerplate offers?
I'd say there are two major ones. First, it automatically detects the program's architecture. Is it 32-bit, 64-bit, ARM? That's essential for formatting your shell code correctly for the target CPU.
And the second big one.
It gives you a really robust I/O framework. This is crucial. The same Python script works with almost no changes, whether you're running the program locally on your terminal or attacking a remote server over the network.
So it handles the switch from local to remote for you.
Transparently. Plus, it has built-in debugging, like showing you a hex dump of the traffic, which is invaluable for spotting errors.
So you've got the template, you've got the connection, but the absolute heart of almost all of these memory exploits is finding one number, the buffer offset.
That's the critical conceptual leap.
So what is the buffer offset and why is it so important?
Okay, think of the program's memory like a long street. The vulnerable program takes your input and puts it in a temporary box, a buffer. If you send too much data, it overflows and starts spilling onto the adjacent property on that street.
And what's sitting right next door that we want to hit?
Often, it's the saved return address. That's the instruction the program will jump to when it's done with the current function. If you overwrite that, you control where the program goes next.
So the offset is just the exact amount of junk you need to send to fill the buffer and then land perfectly on top of that return address.
That's it. It's the number of bytes of junk data you need to precisely reach the beginning of that critical address.
That sounds like it could be a really painstaking process, counting bytes one by one. How do the sources suggest finding it efficiently?
There are two great automated methods. The first is to run a script that sends a unique, non-repeating pattern of characters to the program.
And that crashes it.
It crashes it and creates a core dump file. You analyze the core dump, find the 4 bytes from your pattern that corrupted the return address, and the script can tell you the exact offset from that pattern.
And the other way, a more visual approach.
You use a powerful debugger like GDB, usually with an enhanced front end like GDB-PITA. It lets you step through the program line by line and just watch the memory, see exactly how your input is filling up the buffer.
Okay, and here is the key insight from the sources that just simplifies everything for the hacker. Why is the offset you find locally the same one you use for the remote attack?
Yeah, this is a point new hackers miss all the time. It seems weird because of ASLR, right? Addresses change.
Right.
But the key is that the relative distance between the start of your buffer and the return address is fixed by the compiler. If the remote server is running the same architecture, say both are 64-bit Linux, the internal memory layout is identical.
So even if the program starts at address A locally and address B remotely, the gap is the same.
The offset remains constant. You do all the hard debugging locally, find that number, and then you can trust it will work on the remote target.
That's a fundamental time saver. It turns the hardest part into a one-time calculation.
Exactly. Once you have that magic offset number, you just use Pwntools to craft the final payload, your junk data, followed by the new address you want it to jump to.
Now, to bring this all to life, let's talk about a concrete example from the sources. Did TinyCore capture the flag environment?
This is a downloadable VM based on strip CTF, and it has 6 levels of increasing difficulty.
And the CTF is great because it forces you to deal with resource constraints, right?
Absolutely. It's built on TinyCore Linux, which is intentionally lean. There is 0 bloat. Level 00 starts you off with a couple of hint files, motd.txt and tools.txt.
But the immediate challenge is huge. You said it's resource limited, no GUI, no easy package manager. If you write an exploit in C on your own machine, how do you even get a compiler like GCC onto TinyCore?
You have to master that specific environment. You can't just type sudo install GCC. You have to switch to the user, use the command line application browser, search for compile, and then install the compile abstract package. It really forces you to be comfortable on the command line.
And this brings us right back to Netcat. If you write your exploit script on a nice machine with a GUI like Kali Linux, how do you get that file into the TinyCore VM?
This is where that Netcat file transfer trick is just essential. It's so elegant, it bypasses all the complexity of shared folders or anything graphical.
Walk us through that 2-step process again.
Okay, so on the receiving machine, TinyCore, you run Netcat in listening mode. -ncv-lp port file name. It's just waiting, ready to dump whatever it receives into that file.
And on the sending machine.
You just pipe the file's contents into the connection. You use cat file and pipe that output straight into a netcat connection pointed at the tiny core IP and port. The file just streams right across. It's beautiful.
It's a perfect example of combining simple tools. Okay, let's run through the first few tiny core levels. Level 00 is almost a sanity check.
Yeah, it's pure reconnaissance. The password, EASCOD, is just in a hidden file, home level 00.password. It teaches you to use LOC to look for hidden dot files.
Level 01 then escalates to basic programming and permissions. The goal is to write a program that can read the password for the level 01 user.
Right, so this gets into file permissions, ownership.
Yeah.
You have to make sure your program executes with the right privileges to read that protected file.
And level 02 pivots completely. It's a web challenge.
It is. You're accessing a service on a web port, and the goal is to force the web server to read the password file and display the content. Classic file inclusion vulnerability.
So you're not attacking memory, you're tricking the web app's logic.
Exactly. You have to manipulate the HTTP request itself, maybe a cookie or a URL parameter, to trick the server's file reading function into grabbing the password file instead of the normal web page.
And for that, you'd use a tool like Burp Suite or OSBCP.
A proxy that sits between you and the server, letting you intercept and modify the traffic. Classic web pen testing.
But levels 03, this is where the complexity really spikes and ties back to everything we've been discussing about binary analysis.
Yes. The password is on Gaima, and the challenge is a binary called level 03. The hint talks about a negative index.
So what's going on here?
This is a deep dive into binary exploitation. You have to inspect the source code, level 03.c, and you'll find an array called fns.
And what's in that fns array?
It's an array of function addresses, basically a lookup table. Input 1 might call the print string function, input 2 might call delete string.
So where does the negative index come in?
It suggests a vulnerability where the program lets you read or write to memory before the start of that array. The solution requires finding the offset to a hidden or deprecated function somewhere else in the program's memory.
So the exploit isn't about injecting new code, it's about making the program jump to a function that's already there.
Precisely. You use the concept of the offset to calculate a negative index that points directly to the memory address of, say, a hidden run function that prints the flag. You'd use GDB to map out the memory, or you might script a brute force attack with Pwntools to try different negative indexes until you hit the right one. It's a synthesis of everything.
So what does this all mean for our listener? We started this deep dive trying to understand the hacker's toolkit, and what we found is that CTFs are this comprehensive training ground.
Right. It combines network setup with netcat, rapid prototyping with Pwntools, and that deep analysis of program architecture, finding that critical offset.
Which is that capturing the flag isn't about some kind of magic.
No, it's about methodical, detailed understanding of how systems work. The tools just automate the execution. The real intelligence is knowing where and why to strike.
It really highlights that the person who wins isn't the one with the fanciest exploits, but the one who can analyze a small C program like in level 03 and manipulate its internal memory layout.
Which brings us to a final thought for you, the listener. Consider the sheer effort involved in mastering a challenge like level 03. While tools like Pwntools make it easier, that fundamental understanding of offsets and function arrays is what truly defines an expert. So I encourage you to think about what other hidden array or memory structure vulnerabilities might exist to the systems you use every single day, just waiting for the right offset to be discovered.